zoom into 4.7. I just apologize. It never showed up on the screen. That was totally my bad. I'm going to come back and explain this guy up here, this graph that we see, in just a second. But first, let me go ahead and actually come down to what you guys were supposed to get in your graphing calculator in radian mode. Okay. I'm going to actually, because I don't have a calculator, I didn't pull it up. I was magically doing sneaky stuff back there with my calculator. I was just sending a school email. But back here, I'm going to actually think about this guy for a second. Not that guy. This guy is a sine. I could think about him. 1. Three, so it's been horizontally shrunk by a factor of 1/3. I could think about that for my sine in a second, but right now I'm going to think about him. Exponentials swoop. Do you remember that? Yeah. Logarithms are like what would that be called? A leveling off swoop with a vertical asymptote and like getting flatter, 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 flatter. But exponentials swoop up, exponential growth and decay, super fast, super high. But this isn't any exponential. It's an exponential that's been negative on the inside, flipped on the inside by the x. So it's not going to swoop this way. It's actually going to swoop down that way. What if I were to show you a sketch? And actually, to be honest, exponentials, because you guys are in Zoom standard, they hit the axis at 1, which would be way down here if you guys have it up to 10, like Zoom standard. So actually, it would be more like this. Now, hold on. On a asymptote, it actually wouldn't cross the axis. It would just get closer, closer, closer. In a way I can't even show you. It gets so close, like you'd have to zoom in, zoom in, zoom in, and it would still actually show you. If you guys remember sine alternates between positives and negatives, up to +1, down to -1. It just goes back and forth and back and forth and back and forth. If I'm multiplying by a sine, which goes back and forth between small negative and positive numbers, he's actually going to make the exponential guy bounce too. And if he bounces, he's just going to be this guy. He's actually also going to be, let me get my little -1 marked, also going to be this guy. You can't even see it. And I know it might be hard because exponentials get really high really fast. But if I was able to make this window in a way that you were able to not only see the super small numbers, but also the super big numbers that e becomes when you raise him to higher and higher and higher powers. E is 3-ish at 1 would be here, 3-ish at 2 would be 9, which is already the top of your window. 3-ish at 3-ish would be 3 cubed, would be up to 27. You'd have to make your window go actually super, super high. So some of you might play with that, and you might actually try to get your window go up to like 100 or something. Up. Don't zoom out, because if you zoom out, it zooms out the x's too, which gets confusing. Have your y's go +100 or +1,000. You might see more of this than what you could in just a 10 by 10, because a 10 by 10, you can only go to x equals 2, and then already you're maxed out. But ultimately, you actually have a sine curve. Just guess what the sine curve is doing. It's bouncing between the boundaries, not of a sinusoidal axis. Well, it does have a sinusoidal axis, actually. It does have a sinusoidal axis, but it doesn't have a set top and a set bottom, because that exponentially guy allows, oops, sorry, it should actually go through the origin. It's a sine. Hasn't been translated. There we go. The exponential function changes his upper and lower boundaries. Now, you guys sadly probably only saw like one little swoop. You probably didn't even see the oscillating because they get so small so quickly. This is like squished in. This is horizons. So what's going on up here with this guy? You guys might not have seen it, but this is the graph of f of x equals x sine of x. This is a no, right here. The old graph? What's negative, bud? No. It's x sine of x, buddy. Are you in radian mode? Oh, you're trying to look at the graph on your calculator? Is that what it is? Okay, let me come back and see it in just 1 second. But hold on, let me set up what's going on. I can see maybe what went wrong or what's kind of funny. As you graph, just like down here, you have boundaries based on this guy expanding sine's horizons. And when you expand sine's horizons, you have your, if I can get my red marker put away, forming the boundaries of sine. But not just x, because sine oscillates between positives and negatives, actually also negative x. Now this might seem a little bit weird, but when the sine makes, how can I put this? When you plug in negative x's, and the sine is also negative, and negative times a negative is a positive, it actually ends up letting sine bounce back and forth in between. Sine is negative, so what would, it's flipped and reflected. So this guy is just a little bit weird because here's the sine starting in the middle. He's bouncing between my x and negative x boundaries. But because of the nature of a negative times a negative, he actually ends up flipping over here. But either way, do you guys see how the sine curve horizons are expanded? So whenever you multiply a trig function, especially a sine and cosine, the waves, whenever you multiply a wave by another function, it actually ends up changing. You still have a wave, you still have the oscillations, but all of a sudden, life can get a bit more, or these functions, these waves can get a bit more practical. Because remember back at the very, very, very beginning of us talking about waves, my illustration was dropping a pebble in a pond. This picture right here, right? But we talked about the idea of, wait a minute, sines and cosines aren't very practical because what do they do forever? They continue forever up, forever, never, sorry, always going between 1 and negative 1, never dwindling out. But what do actual ripples in ponds do? They dwindle out, right? But is there a way to mathematically try to model that also? And the answer is, yeah. We can have waves dwindling out when we put other math functions with them. Now, we're not going to make you guys do that and figure that out and actually make this a ripple on a pond, because a ripple on a pond probably wouldn't go that way. But you could start it here. And you can actually multiply this to make it a little bit wider, a little bit more expanded to let the wave go a little higher. Make the waves dwindle out. You just put other functions in and multiply. That's called dampening or damping the function. Have you guys ever heard about dampening the sound? Like sometimes in recording studios, they're going to have a lot of insulation in the walls because they're trying not to, blast the music to everyone around them, or they're trying to have multiple recording studios, etc. But anyway, dampening the waves. Hey, that was just a little effort at the end of the section. Joe, I'm going to come back and see what was going on with your calculator, and as I do, we're going to start grading. Did it work out? It's good? Okay, cool. All right, guys, section 4.6, let's go see how you did on tangents, cotangents, secants, and cosecants. Starting with 10 and 12, and 14, which are all matching. Let me see if I can zoom out just a little bit so we can see all three at the same time. 10 ends up being C. Sorry, number 10, it's right up there. But 10 ends up being C because of his period and his amplitude. Number 12 ends up being D. Number 14 ends up being B. C and D and B. C and D and B. Number 22, how do we graph a cosecant? We bounce him off of sine. So your sine curve started in the middle with an amplitude of 3. Sine curve starts in the middle because D is 0. Amplitude of 3, going up 3 and down 3. Your sine's period ended up being 2 pi over 4, which is pi over 2. So sine would have finished in pi over 2, would have been halfway at pi over 4, would have been 1/4 of the way at pi over 8. Now, they made a snazzy table, and they were like, hey, look, you have your pi over 8, and then you have maximums and minimums. But remember, you guys don't need to be listing the points. You just need it clearly shown in your graph. Did you guys have your sine curve go into pi over 2 for a cycle? So hence your cosecant bouncing off of 3 and negative 3 at pi over 8 and 3 pi over 8. Pi over 8 and 3 pi over 8. You didn't have that table. Number 28 was a cotangent one. Cotangents, you take the insides, you find their vertical asymptotes by, I think I want to show you guys this one. My way, not their way, because remember, I'm not making you make a big old table. You steal their graph, but let me show why. We would have taken this, and according to our notes, we would have found our VAs by taking pi x over 2 and saying, you're not allowed to equal. Do you guys have your notes close, or did you kind of get this down yesterday? Cotangents, vertical asymptotes. Were they at the pi over 2s or at the pi's? Cotangent in your notes. Asymptotes. Were they at the pi over 2s or the pi's? Which one? Yeah. Do you see them in your notes? They're at the pi's. So he can't be pi in. So then we would solve for x by multiplying by 2, dividing by pi, and guess where your vertical asymptote should happen? Every 2. Every 2? Yeah, because 2n means every multiple of 2. Start at 0. 0, 2, 1, 2. Could have kept going. The next one would be at 4, right? The next one would be at 6, 8, 10. You're going to have every in the right direction and the left direction. So where do your points of inflection occur? At D, which is just 0. They've been vertically stretched. So should you have one that's super, 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 super like level off? No. It should be a little bit stretched. Am I going to make that a huge deal? No, not a huge deal. But it is something to keep in mind. Once again, did you have to do the table? No. You need the vertical asymptotes and the points. Number 40 was, hey, can you use your graphing calculator? But do you guys see how a vertically flipped tangent looks an awful lot like a cotangent? The 2 made it so that it was squished in, so you would have more tangents in this interval than you would normally have. But tangent still always straddles the y-axis unless it's been shifted, unless there's a plus or minus. It's going to straddle the axis, whereas cotangent is always apart or next to the axis. Something to keep in mind. 48. You were using your calculator on him too? Mm-hmm. Do you guys see what you would have needed to put in your calculator? There's a couple different ways of doing this, but some of you, hopefully, you figured out that secant is 1 over, I can't draw on this, sorry. That secant is 1 over cosine, which it is, but the 1/3, you could have had the 1 over 3 cosine. There's your 1/3. Or you could have literally written this like, that doesn't help, sorry. Could have just done 1/3 times 1 over cosine. And cosine in your calculator automatically puts, then we just throw all that stuff in the parenthesis and then we're okay to go. But once again, because degrees would have been a whole lot trickier because the numbers are way bigger with the angles. Okay, anybody having struggles on your calculator? It's working off? Or it's working out okay? Real quick, would your zoom standard have been zoomed like this to the scale? You would have had like 10, negative 10, and negative 10 and 10. How close would these have been on your calculator? Yeah, they would have been squished. You would have like barely even seen the space. Because 2 and negative 2 would have been really, like it would have gone up. Sorry, that's not even 2. What is that?
It's like half. Oh,
Why is it a third? Because of the amplitude, right? So if you guys were looking at it, it would have looked almost like these were on the axis, but were they? No. Just the sine curve only went up to 1/3. Cosine curve only went up to 1/3 and down to negative 1/3. Just be careful that you know what's going on. 56. was a little bit weird in that they were asking you to find the intersections between these two guys. So he could have been one graph, which they did do, a cosecant graph bouncing off of a sine. This would have been some awkwardly random number unless you guys realized it was actually a unit circle number. Why is negative 2 root 3 over 3 a unit circle number? Isn't this one of my special sines and cosines? 1 over if it's a reciprocal. 2 over rad 3. But what do you still have to do? Rationalize. And so when you rationalize, this is one of our unit circle-y ones. So this one you were trying to figure out, at what angle will cosecant be this? Hey, it's the same thing as when sine is negative root 3 over 2. All students take calculus. Sine is negative in the 3rd and 4th quadrants, which is why it didn't happen between 0 and 180. Both of these intersections happen between 180 and 360 at the pi over 3s. Number 58 just had to do with, I think, the odd property of tangent. Is that right? We wrote down those formulas in section 4.2, if you guys remember, or 4.3. Had to do with the odd property of tangent. It's one of those identities from earlier on in chapter 4. But if you guys look at him, we talked about it in class. He's an odd or origin symmetry guy. He's an odd or origin symmetry guy. 70 was literally as easy as graphing him and seeing how many graphs. When we graph two things, don't we usually see two graphs? They're the same thing. And we're going to build more on that in chapter 5. They're the same thing. Well, that's weird. I think I'd much rather see G than F. F looks yucky. G looks kind of basic. And then number 76 and 80, you guys were allowed to go to your graphing calculators for both, but maybe now you at least have somewhat of an idea as to what's going on. This guy right here that's being multiplied is dampening or is changing the boundaries of sine. So this little guy out here is the 2 to the power of blah, blah, blah. But what it's doing is it's having sine, and sine's just kind of cycling inside this guy's top and bottom original graph and reflected graph. And all they were asking you to do is super snazzy math language. The arrow just means approaches. Is like, hey, what's going on as sine goes that way? It's leveling off, aka the wave is going to 0, or the height of the wave is going to 0. But here was another way. This one actually is, since you're multiplying, I know it's division, but division is multiplication by a reciprocal. I can show you this one super fast. Long story short, how is this one dampening? You could rewrite this as 1 over x minus 1 over x times cosine. There's that dampening right there. And if you guys remember, 1 over x, didn't he look like, oh, sorry, I didn't do it very well. Yeah, 1 over x is squeezing him in. Okay, questions on evens or odds? I have it ready. Jason.
63.
Cool. Anything before 63? Going once, going twice. Should be easy to find because you marked it with question marks. Okay. Where's 63? Oh, there he is. He's hiding. Oh, nice. Okay. From what we just saw, actually, can you guys tell this is going to be a dampened one?
No. Oh, yeah.
Not just the trig. Now this one's kind of hard. It's a cosecant, so a bouncy one is getting... But they didn't ask us for necessarily making the graph by hand. So this would have been one, Jason, that I would have told you to go to the graphing calculator. The dampening ones, we're trying to get somewhat of an understanding. You're not going to have to do them by yourself. I'm just going to go ahead and stick with the verify algebraically, just because in my head it's easier than even going to the graphing calculator. You know, symmetry is based on plugging in, asking yourself, what happens when you opposite? That's going to be odd. Neither, that's going to, well, be neither. And that's because even had this little formula where it stayed the same. When you plug in a negative, there was no difference. Opposite had the formula that when you plug in, the formula is now the opposite of what it was. So this guy, if I plug in a negative, and I plug in a negative to this x. Now, you would have had to go to those properties in section 4. I wish I remembered. I think it was 4.2 or 4.3. Maybe 4.3. We talked about the graph of cosecant. Just like normal cosecant. Cosecant bounces off of sine, right? So maybe you could actually think to ask yourself, is he odd or is he neither? Does he flip across? No. Down. Yes. Cosecant is, so what's going to happen to cosecant when you plug in a negative? Yeah, it will be, oh, sorry. It will be the opposite. But then he by himself is odd, but when you put an odd, it's going to be even. Now, with numbers, because 3 times 7 is an odd times an odd is an odd, but an odd in which switches to negative times an odd function which switches to negative is actually going to end up being even. Yeah, does that kind of help? There are those formulas in that one section that has like odd properties of trig, but once you know the graph, you can kind of use the symmetry to help out. Anything past 63, going once, going twice, sold. That didn't work. Now it's sold. Sorry, this is the page of notes that you weren't able to copy down when I awkwardly thought you were. Lo siento. Just in case someone else has like a quick test correction at the end of class, the stapler's still there waiting for you. But after that, I'll close it up and get it turned in. My kiddos that are absent, Tyler and Priscilla, if you're listening to this, just get me your test on Monday. Your test corrections, and remind me you were absent. If you guys remember from when we talked about this last time, inverses last time. Inverse functions, they have a snazzy notation with a -1. Which in your calculator is actually kind of nice. You guys are used to the second sine, second cosine, second tangent buttons. It's the second sine, second cosine, second tangent buttons. But inverses are not the same as the reciprocals. But before we get to that, today we're only going to get to inverse sine. That's totally okay, because if you guys check out, it's not due until Tuesday. All inverse functions are built off of original functions. So I'm going to get the original sine. Just 2 quick little cycles of it. The original sine, so y equals sine of x. Let's see if we can remember how inverse graphs are related to original graphs. Let's see if we can remember real quickly how inverse graphs are related to original graphs. They reflect over what? No. No. You guys are right in between. You're both saying something that's wrong.
Origin.
Y equals x. Y equals x. They're the ones that reflect across the diagonal line y equals x. Which, in a way, doesn't seem like that big a deal until you get like a really tricky sign. But maybe some of you can actually realize, okay, if I flip it piece by going in a very similar fashion, instead of around the x-axis, it's going to be going around the y-axis. Now my reflection is a little bit messy. I'm trying to make it just a little bit nicer. It shouldn't be quite that wide. Let's see if I can get it a little bit better. It should be leveling off right about there. There we go. And it should be leveling off right about there. There we go. But what's the problem with that? Is that a function? The squiggly one, the snaky one, the green one, the inverse one, is that a function? No. What does it fail? What test? Oh, stink. It fails all over the place. So the ironic thing is, if you guys look at the title, it says inverse trig what? Functions, but they're not functions. And actually, if you flip all of them, if you flip cosine, he's going to do the snaky thing too. If you flip tangent, it's going to be a guy on top of a guy on top of a guy. He's going to fail. Cotangent, hold on, sorry, he goes down. It's going to be a guy on top of a guy on top of a guy. He's going to fail. So this is the key. All inverse trig functions, we're not going to necessarily do it. It's something for us to understand, are actually all cut down. So let me show you who inverse sine really is. Let's see if I make it a little bit better. It's kind of like the flipped mountain to the valley, minimum to the maximum, and that's it. But it stops. It can't keep going, because if it kept going, then it would start going. So what it is it's cut from here to here. It's just a piece. But ironically, that piece, because it goes between -1 and that's weird. Those were never the x's of trig. Those were the y's of, wait a minute, don't the y's of the inverse become the x's of the original? So normal sine went between 1 and -1. So sine inverse goes between, well, his x's go between -1 and 1. And the y's, since everything flips, is going to go between angles, but not all angles. It can't go from 0 to 2 pi or from -2 pi to 2 pi. It actually can only go part of that. So you guys notice this is a full cycle of sine, and I can't have that full cycle. That would be 2 pi. But I can only go not even halfway. I can only go a quarter of the way. A quarter of the way is pi over 2. So my domain goes between what used to be the top y, bottom y, and my range goes between, for this cutoff piece, what used to be the x's or used to be the angles. So for inverse sine, I actually have the x's being my ratios and my y's being my angles. My x's are my ratios, y's are my angles. And ratios for sine, quick reminder, are going to be opposites over hypotenuses. That's what we were always doing when we did 1/2, root 3 over 2, and root 2 over 2, and 0 and 1. We were doing little ratios. We saw later the triangles and how we could use triangles, but unit circle, the original sign, the x's, the ratios were the ones. Now they're flipped. This is going to be f inverse of x, or sine inverse of x. Call it f inverse if you call y equals sine your f. You could call it f inverse, but they're actually just going to call it y equals or f of x equals. We're talking about the inverse. We're not really going from sine to straight there. So this is sine inverse. Now we just barely scratched the surface of how the x's of the original became the y. But graphically, this is how it works, and graphically, this is why, with that whole vertical line test and the failure of it, I'm about to make a big deal about this guy. Because to some extent, we're kind of used to this guy. This guy at all. We're kind of used to sine of x can only be between 1 and -1. We're kind of used to that. And if I say it in class and bring it into a problem, you'll be like, okay, I kind of remember that. Sine only goes up to 1 and down to -1. But this guy is like completely new. That we can only go up to 90 and down to 90. We can only look in quadrants 1 and 4, but not even normal 4, like going up and going down, going backwards through 4. We're not going to be looking at 2 or 3 at all as far as our quadrants and answers that need to come out. So if you guys have your graphing calculators, I want you to go into degree mode just because it's a little bit easier for us to think in degrees. I want you to go in degree mode. I want you to hit second sine, which brings up sine inverse, right? And it's going to look like just what this one says inverse sine looks like. Sine -1. Remember, inverse is not the same as reciprocal. Not. Inverse is not reciprocal. So you can't use the second sine button for cosecant. Cosecant or the reciprocal would have to use 1 over sine. Okay, but when you do the second sine button, I want you to, which real quick, that actually can be called arc sine. There is another way of doing sine inverse without needing to have an option. Microsoft Word, or even like Google Docs. You guys in the Google Drive, you can totally put the superscript, but depending on the software, depending on this, that, and the other, it's sometimes hard to do that. And if you put a little caret, it means a power. So they kind of made this other terminology for sine inverse. That is one way, but this is another way. Arc sine means the same thing. I want you guys to go ahead and do second sine of any number. Ready, set, go. Second sine of any number. Someone. Did anybody get it? Second sine of... No one got an error? Sweet. Chris, what did you put into it?
5.
Okay, he put 5. It didn't work. Who else got an error? Sweet. Harana, what did you put in? 7. It didn't work. Who else got an error? Sam, what did you put in? 9. Didn't work. Who got it to work?
Me.
Joe, what did you put in?
Sine of 1.
Sine of 1. What did you get?
I get 90, but I went up.
90. Wait, pause, Joe. Hold on, let him think about it. Sine of 1 is 90. Sine of 1 is 90. Sine of 90 is 1. Sine inverse of 1 is 90. Sine of 90 is 1. Who else got something to work? Who got an answer from second sine of something? Anybody? Only errors? Chris, what'd you get?
100 over 100.
Okay. Second sine, sine inverse of 100 over 100 equals 90. Wait, what's 100 over 100? 1. I want someone who did not put in 0 or 1 or -1 and gets it to work. Who can put in something, not 1, not -1, and not 0 and get it to work? Chris, what'd you put in?
I did 1 over 2 and I got 30.
Oh, he put in 1/2 and got 30. Jason?
I got 0.1 and I got 7.5.
7.75. What else?
And negative 0.5 and negative 30.
Put in -1/2 and got -30. Matthew, you put in?
I put in rad 3 over 2 and I got 60.
Rad 3 over 2. Guess what? Second sine only works when you put in fractions. Why? Because you're putting in the ratios, and what you put in has to go only between -1 and 1. You're putting in ratios, and what are you getting out? Numbers that stand for angles, and all the angles that you guys put in are going to go between -pi/2 and pi/2. Before you leave for the weekend, here's the struggle. Normal trig says, give me an angle, I'll give you a ratio, and some of you had struggles with that in unit circle. Guess what inverse trig says? I'll give you a ratio, you figure out the angle. So before you come back on Monday, you need to really take to heart the following comment. It's not only important to know the unit circle forwards, but some of you need to study your unit circle. Bye. Bye. Study your unit circle. I'm serious. Bye.